Hello everyone. Uh, the next question we are going to take is unique binary search trees part 2. Okay, if you haven't solved the part 1 question, I would recommend it to solve you. I have already solved this and the link is in the description. Okay, so let's try to solve this question. Given an integer n, return all the structurally unique BSTs which has exactly n nodes of unique values from 1 to n. Okay, so what we have to do is, let's suppose n is equal to 3. So how many binary BSTs we can make? Like 1, this is 2, this is 3. This is first. Putting 1 in here, we can also make it like, not like this, sorry. This is not binary tree because we have to create a BST, not binary tree. So if 1 is there, 2 should be in the right, 3 should be in the right, okay? And if 1 is here, let's suppose we put 3 in here, so 2 should be here. Okay. So what we can do is we can recursively start from 1 and it end to n, and we will divide at each I, create a subtree from this part, create a subtree from this part, and from I we will create root and we will link it to the left and right. This way we are gonna do it for every recursively to each and every node. Okay, each and every node, not from 1 to n, every node, because if this is going to cause a subtree, then we have here we are left with 1 dot 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 I minus 1. So again we have to do it on every. Okay, and this will be recursively go went on. But okay, and the base case, we don't have to worry about these. We have to only worry about base case. So what would be base case? When this start, 1 is our start, okay, and this is our end. So when the start and end will be equal, or when the difference is 1 or 2, then only we have to worry about what to return. Okay, so let's try to write some code. So if there will be a start and end, okay, and what we have to do is we have to traverse for I in range. We are going to traverse from start and go till end. Okay, then after that, let's call our function. Okay, so now what we have to do, we have our I, we have our, let's say, now we have our I, and the left will be from start comma I minus 1. We have to create uh, trees from here, the left subtree. Okay, we have to create as many as trees from this part, then, and right part will be I plus 1 comma end. Okay, so, and yeah, let's try it. So we have to call our helper function. Like, what is this helper? It is like generate tree. Okay, this is same as generate tree. Whenever I write helper, it means the same function as the first one. So this, I'm just taking help of this function. Okay, so helper, we are gonna call it on start comma I minus 1. Okay, further we are gonna call it on our I plus 1 comma end. Okay, have I solved this question? Okay, I haven't solved this question. Okay, this will be cool then. So this will return our, okay, let's suppose this will be our all the left subtrees. Okay, this will be our left subtrees. So it will return an array full of left subtrees. Okay, and this will return our array full of right subtrees. Okay, so these both are returning it. Now what we can do is, um, yeah, okay. So we got all the solution from left and right. Then we will create our root node. Okay, let's suppose this is our root node 3 node of I. Okay, it will be I, yeah, I. This will be our root. We have created all three components of a tree. So root dot left. Okay. Okay, what we have to do now? Should we do backtracking? No, no. Let's stick to this directly. After creating the node of I, we are creating it every time. Okay. So this is a reference to I. Okay, this will be a reference. What we have to do, like, for okay, 1 second. We have to think a bit. 6 minutes in the code. Okay. So left subtrees and right subtrees are here. Let us suppose, let's take an example of 1, 2, and 3. So we have our 1 at first, we have our 2, we have our 3. Okay. Then 1 will call on 1 will call on 2 and 3. Okay. And this side it will get none, return an array none. While in this case, and then this 2, 3 will call. Okay, this 2, 3 will be called on 2 and 3. So when it will be called on 2, 3, this will return none and this will return 3. So this will become 2, 3. Or rather I should write it like 2. This will become like this, 2 and 3. So when it got returned from here, we can simply 1 add 2 and 3. Yeah, it will be no problem. Like we can add 1, 2 and 3. So all we have to do is traverse both of them, both of these left subtrees and right subtrees, and yeah, and append them. Will it work or not? 1 second. Let's call it for 2. Is it working here? Yeah, because when we call it on 2, for 1 there are two solutions, okay? So for 3, 2 it will return 3, 2, and for 1 it will return 1. Yeah, it is working. Let's see what will we get. So for I, no, so not for I, for L comma, yeah. So for L in left subtrees, for L root, okay, so let's say for left root in left subtrees. Okay, and same with right subtrees, for right root in right subtrees. Take all the combinations. Okay, right root in right subtrees. This our result tree. Okay, result tree. Result trees. Result tree nodes. Okay, it is initially nothing, or rather we should say none. No, let's put none in nothing. Okay, so okay, and instead of creating it here, we have to create it in here. So let's create a new root in here, and root dot left is now our left root. I guess you are following it. So we have got our answer in left and right, and it will be in the form of array. So we are creating a new array which will return the result. Okay, and root dot right is now, okay, root dot right will become right root. Now what? Now we have to append this result of tree nodes dot append into the root into result of tree nodes. Okay. And at the end, what we have to do, we have to return result. Okay, 1 second. Yeah, so we are going to left and right, then okay, yeah, it should work. Okay, return res of tree nodes, and we can't use dp in here too. Okay, this is good. Now what? So it appended root, no problem. Now again root is defined to a new location, tree node of I, and every time it is returning root. So now we have to deal with base case only. Okay, so let's take base case. So if start is equal to end or what? Yeah, if start is greater than end at first, then return an array full with none. Return an array none. Yeah. Else if start, yeah, not start. Let's say end. Yeah, start is equal to end. If this is the case, then what should we do? So left is 1 and 1. So return a node containing, return a tree node of start. Cool. And if start, uh, what if start is greater than? Okay, let's stick with it. Okay. Let's try to run our code and see whether what's the result now. So let's let's call it return helper of start comma end. Start will be 0, end will be 1. Sorry, start will be 1 comma n. Oh, it got accepted. Nice. So let's try it on 5. Ooh, yay. Finally, it got accepted in one, in a single time. This is good. This is great. Okay, let's submit it then. Can n be equal to 0? Okay, no. I guess you have understood the concept behind it. I have taken left and then right, then root is itself. I'm creating root every time, because if I would have created root here, it will point to the same reference. We have to create root new time every time, and then we have to append it inside. Okay. Well, this was a medium question, not that much great, but still we were able to do it. We will do more questions. Subscribe for more questions, and we will meet you soon. Okay. Bye. Thank you.